Good morning, good afternoon, and good evening, everyone, depending on where in the world you're dialing in from. And welcome to today's webinar. My name is Maria. I'm the Director of Demand Generation here at Cockroach Labs, and I will be your host and moderator today. Now, quickly, before we get started, I wanted to let you know that we are recording today's webinar, and we will send it out in a follow-up email. We'll also post a blog post with a summary and key takeaways, so you can just sit back, enjoy the webinar, and join in on the conversation. And you can do that by submitting your question in the Q&A control panel, or you can tweet at us. My colleague Jessica is here behind the scenes, and she will handle your questions one-on-one during the webinar. And at the very end, we will leave it open for a couple more live questions. I'm also here with Alex Robinson, today's speaker. Alex is a member of the technical staff here at Cockroach Labs, where he works on CockroachDB's core transactional storage layer and manages all integrations with orchestration systems such as Kubernetes. This involves both running Kubernetes clusters directly and working with end users to ensure that CockroachDB works well within their varying orchestrated environments. Previously, he was a senior software engineer at Google, where he spent his last 2 years as a core developer of Kubernetes and GKE, with a focus on logging, monitoring, cloud provider integrations, networking, and reliability. So we have a packed agenda for you today, and let's just get started, and I'll kick it right over to Alex.
Good morning. Thanks for the introduction, and let's get right into it. My name is Alex, and I'm going to be talking, as you probably assume, about running a distributed system across Kubernetes clusters. And if any of you have run Kubernetes clusters recently, over the last year or two, you've probably found that it's a pretty nice way to run your distributed applications. It gives you a whole lot of great things and makes it easy to run even pretty complicated applications like a distributed system. But if you'd tried doing this a few years ago, you'd know that Kubernetes has come a very long way over the last 2 to 3 years. If you'd wanted to run a system 3 years ago, you would have had a really tough time running anything that has data in it. You're missing out on features like volume provisioning and stateful sets. There weren't any multi-zone clusters until a couple of years ago. As someone who tries to make it easy for other people to run my application on Kubernetes, meaning I want to make it so that other people can run Cockroach on Kubernetes, innovations like Helm charts and operators have been great developments in the community as well. And as an end user using Kubernetes, it's great that there are more and more managed Kubernetes services these days that make it so that you don't have to run your own cluster. However, things haven't really improved if you want your service to span across multiple regions or multiple Kubernetes clusters. Very little community developments have happened since the creation of Kubernetes in order to make this a better experience. There have been some early efforts, such as the Kubernetes project, or that was Kubernetes without a K, and the recent Federation v2 project is still ongoing. But nothing has yet solved the problem of trying to run a distributed system that spans multiple clusters. It's still a very hard experience that isn't really documented at all. You need a lot of expertise to kind of even know where to get started. You might ask why you would even want to run a system across multiple regions, though. Maybe there's a reason that this work hasn't been done by the community. And I'd argue there are two big reasons, and maybe some other smaller ones as well. The biggest reason is user latency. The further away your service is from your users, the longer it's going to take for them to get their responses back from your service. And the faster your service is, usually the more people will engage with it, the more time they'll spend with it, and the happier they'll be. This is especially critical if you're running a global service that has users all over the world. If you don't have any instances of your service near them, they're going to have to wait hundreds of milliseconds to get responses back from your service. So this is a very strong reason for wanting to run whatever you're running across multiple regions. As well, fault tolerance becomes very important. You want your application to continue running even if an entire data center or an entire region of data centers goes offline for some terrible reason. And so in this case, if the data center over in California goes down, the users on the West Coast might have to wait a little longer for their responses, but they'll still be able to use your service because of the other replicas that are stood up on the other parts of the country. And there might be bureaucratic reasons for wanting to run a system across multiple regions. There are many laws in many countries now around where you're allowed to store users' data without their permission. So if you might have to store the data from users in China, and you might need to store the data from users in Russia. And having a system that spans multiple regions enables you to do that. If you only have a data center in the US, then you're going to have a tough time. And so for the bulk of today, I want to talk about the practical experience of running a distributed system across multiple Kubernetes clusters, and what it's really like. And we're going to cover why it's hard, what kinds of detailed information about Kubernetes or about your distributed system you should know before you get started. And then we're going to look at some solutions that we've put into production in various environments and seen work well for us. And just so that you know where I'm coming from, my experience with Kubernetes it goes back quite a while. I worked directly on Kubernetes and the Google Kubernetes engine from mid-2014 for about 2 years. I was part of the team that launched GKE in the first place. And while I was there, I worked on cloud provider integration, networking, logging, monitoring, a whole bunch of things in Kubernetes and in the managed service as well. And since then, I joined Cockroach Labs to work on CockroachDB. And in addition to working on the performance and reliability of the database itself, I also have worked on all container-related efforts for us. So that's meant creating multiple configurations for different orchestration systems, helping people run them in all sorts of different environments, whether it's single zone or multi-region. And also, even though my goal is to create configurations that can be universally used by pretty much anyone, there will still be some users at the edges who need to do things their own way for one reason or another. And I also end up helping them with their more custom setups. So my goal is to standardize things, but I also understand that not everyone can use the standard solutions and get to see some of the edge case solutions as well. And so the question of why it's hard is something that many people might not even think to ask. I've had a number of conversations with folks where they'll assume that since CockroachDB runs really well across regions, and because Kubernetes makes it really easy to run CockroachDB, that it's just naturally going to be easy to run CockroachDB across multiple Kubernetes clusters spanning regions. But in fact, it's not easy at all. It's significantly harder than running Cockroach in a single cluster. And some of you might have noticed that so far I've been using the terms multi-region and multi-cluster essentially interchangeably. And that's because Kubernetes is not designed to have a single cluster span multiple regions on the wide area network. For quite a while, it wasn't even recommended to have a single cluster that spanned multiple availability zones within a region. The community fought for that, and so that's now a recommended configuration. It's called a multi-zone cluster. But trying to run a single Kubernetes cluster that spans regions is definitely at your own risk. It's not something anyone I've ever known would recommend. And so I'm going to keep using these terms mostly interchangeably. But what this means is that if you want to run something like CockroachDB across multiple regions, you are necessarily going to have multiple Kubernetes clusters, at least one in each of those regions. And to better understand the problem of setting up a system like CockroachDB across multiple regions, it helps to understand what does a system like Cockroach or any other stateful service need to run reliably in the first place, because we're going to have to provide any of those things. And today we will be using CockroachDB as our example. It's by far the system that I'm most familiar with running in Kubernetes because I've had to do it for a couple of years now. And CockroachDB, for anyone who isn't familiar with it, is an open source distributed SQL database. Your applications can talk to it as if it was Postgres, but all of your tables and all of your data is going to be sorted by key and split into chunks. And those chunks, called ranges, are then replicated across the cluster so that there are multiple copies of them. As nodes get added to or removed from the cluster, all those ranges will get automatically rebalanced. And we use a consensus protocol to ensure consistency and strong levels of isolation between transactions. And when you do want to run Cockroach across multiple regions, we provide this feature known as locality, where you can tell each node where it's running, and it'll use that information to try and distribute your data across as many fault domains as possible. Or you can tell it to put some of your data only in certain localities, if there are regulatory or performance reasons for doing so. But CockroachDB is one of the easiest stateful systems that you can run in Kubernetes. It's very, very flexible and forgiving. All of the nodes are the same as each other in a sense. There aren't any special binaries. There aren't any special roles. Clients can talk to any of the nodes. All of the nodes serve exactly the same role within the cluster. But Cockroach requires roughly 3 things in order to run reliably. Every Cockroach node has to have some sort of persistent storage that will survive across restarts of that process. Each node has to have a network address that it can advertise to the other nodes so that they can talk to each other reliably. And that address ideally should survive restarts so that you're not always changing addresses. And each node can communicate directly with each other node. So the second point here is we can kind of be flexible about. CockroachDB actually will work if your nodes are changing network addresses. But this is something that most stateful systems need, and so we'll leave it in here for the sake of completeness. So this is a fairly generalizable list. There are a lot of stateful systems that need these three things. And Kubernetes provides these all very well within the context of a single cluster. You might have heard of the controller known as a stateful set, and it was designed to provide exactly these three things. The Kubernetes stateful set gives each node its own disk, or multiple disks. It gives each node its own address, and Kubernetes itself guarantees that all pods can communicate directly with each other. But across multiple Kubernetes clusters, we definitely lose number 2. There's no cross-cluster addressing system. And we often lose number 3. It's often not set up such that a pod in one cluster can talk directly to a pod in another cluster. That's what we might call pod-to-pod connectivity later in this talk. And so the core problem of running a multi-region system all comes down to the networking. You might not have pod-to-pod communication across clusters. You might have to communicate across separate private networks in order to talk from one cluster to another. For example, if you're on AWS, each Kubernetes cluster is going to be in a different region and thus in a different VPC. And so you're going to have to connect those together with some sort of VPC peering or a VPN. And this is going to be even more true if you're spanning multiple cloud providers. And finally, we also need a persistent address that works both within and between the clusters. We could weaken that last point to have 2 separate addresses. So one that works within the local cluster and one that works between them. And that'll be fine as long as your system is sophisticated enough to handle having separate addresses like that. So that will work for CockroachDB, but wouldn't work quite so well for many other distributed systems that assume just one address per node. So networking is the problem. And the question is, why is it the problem? What's the deal with it? How come this multi-cluster case just has no support? And if we go back in time, Kubernetes specifies a list of requirements from the network. So each pod running in a cluster has to be given its own IP address. And that IP address has to be something that the pod itself sees inside its container. And it's the same IP address that other pods in the network see it as. So a pod doing an IF config should see the same IP address as the pod that it sends a network packet to. And all pods can communicate directly with each other without any form of NAT. So no network address translation should be needed. And this is very different from how, say, Docker was doing things at the time, and even how it typically does things now. So Docker would typically give each container on a node its own private IP address, but that private IP address only works on that one machine. And then some sort of NAT is needed for cross-host communication. This is also different from how networking worked inside Google for their Borg system, where each pod just shared the host machine's IP address and was given its own set of dynamically allocated ports. This was a pretty revolutionary idea. And so they laid down these requirements very firmly, saying a Kubernetes cluster needs to have these things, otherwise it's not a compliant Kubernetes cluster. But this posed a real problem because we want to run a lot of pods on each machine, but traditional networks only allocate 1 or 2 IP addresses to each host in the cluster, or to each host in their network. So we needed some way of creating new IP addresses for each of the pods on these machines. And it turns out that there have been a lot of solutions dreamt up over the last few years to satisfy those requirements. There are dozens of solutions out there. And while you can group them into a few classes, they all have details that differ from each other. And so you have tons of different solutions out there, all of which are being used, which means that you can't really rely on implementation details to be true in any given Kubernetes cluster. Say a cluster that works on GCE might be working a little differently than one that runs on AWS versus one that runs on-prem using a particular piece of networking software versus one that's running in DigitalOcean using some other networking software. And because the multi-cluster scenario is left completely unspecified, all those little implementation details of the different networking solutions become really critical because they aren't trying to provide any sort of guarantee about how multi-cluster works. So the way that multi-cluster works is completely left up to the implementation details. It's kind of when you're running a C program and you hit some undefined behavior, maybe it'll work for you on one C compiler and one architecture, and maybe it won't work for you on the other C compiler and the other machine architecture. So this is a really bad combination that just means using multi-cluster is a bit of a minefield because you won't know exactly how the network underneath you works unless you know exactly which network you're running on. And there are a lot of networking solutions out there. These are just a few of them. And again, they all work differently. So there's only so much in common that you can depend upon them. And that means that any solution you end up using may have to depend on your networking provider, which is really frustrating from my perspective, where I'm trying to make configurations that everyone can use. That's not something that's very easy to do when everyone is using different networking providers. And so we can kind of group them into three categories, where some of them do enable direct pod-to-pod communication across clusters out of the box. GKE has always done this. Amazon's Elastic Kubernetes service has started doing this as of earlier this year. They changed their networking model a bit to make it possible. I don't know if this was directly their goal, but their change to using elastic network interfaces and like floating IP addresses made this possible. And others don't have it on by default, but make it fairly easy to enable. So the Azure Kubernetes service, you have to turn on their advanced networking mode to make this possible. And there's a overlay network provider called Cilium, which offers a simple feature known as the cluster mesh, which makes it really easy to turn this on, even if it's not there by default. But in many other networking solutions, it can be quite difficult. And this is especially prevalent for on-prem clusters or for situations where you want to span multiple clouds. So this is a tough problem. And there's a wide space of networking providers being used under the hood, so it's unlikely that there's one single solution. But let's take a look at some of the options for what we can do. And unfortunately, all of the options have one problem or another. And I did most of my work on this in the first half of the year, so it's possible that some development has happened here that I haven't heard about that gets rid of some of these cons. But as far as I've seen, I've been keeping up and trying to play with things every once in a while, and I haven't seen a great solution that's fully mature yet. Work is being done on it, though, which we'll see later. And so, some of the solutions don't work in certain environments. Some of them, break very easily if the operator of the clusters isn't very careful about what they're doing. Some of them use a slower data path, and so you're going to have a less performant system if you use them. Others don't work well with TLS certificates, so you might have to run your cluster in what we at Cockroach call an insecure mode, where you aren't relying on certificates to secure all communication between nodes. Yet other solutions rely on an immature or very complex system that isn't quite ready to be used in production yet, even if it's on the right track. And those systems in particular, the new systems being built, have been improving throughout the course of the year. So I do think there's a lot of promise in the future in the next year or so for like good solutions that you can depend on for this. And again, my perspective on this is likely different from many of yours, just because my goal is to help customers run Cockroach across their diverse Kubernetes environments. If my job was to just get this working within a single stable environment, I could pretty easily identify which one of the many solutions works well for it, and then just go with it and be done. So this is made a little tougher by the fact that I'm trying to come up with some sort of universal set of instructions. And note that for most of these solutions, I'm assuming that in each Kubernetes cluster, you're just going to run a stateful set, and then you're doing something to like connect their networks together. And so then if you wanted to scale up the nodes that you have running in one Kubernetes cluster, you would just scale the stateful set that's running there, and vice versa if you wanted to scale the nodes running in one of your other clusters. There's only one exception to that, which we will look at first. So let's look at that one. So one way to do this is to pretend that you're not really using Kubernetes at all. So Kubernetes allows you to statically place pods onto specific nodes, or you can use what's known as a daemon set, which just puts one pod on every node. And then you can use the HostNetwork option in the config file, in the Kubernetes configuration file, to tell the pod to use the host machine's network directly. So it will use the host machine's IP address for all of its communication. This means that your pod will be using the ports directly on the host's network. So you can't have more than one Cockroach pod on that machine, because you're going to run into port conflicts if you do. But this means that you can use that host's IP address to communicate between nodes in different clusters. And so as long as you've set up your network such that your VMs or your physical machines in the different clusters can directly talk to each other, then Cockroach pods on those machines will be able to directly talk to each other. And in order to avoid changing addresses all the time and potentially like getting some sort of split brain situation, you're probably going to want to statically assign these pods to machines. So either by directly in the config file saying which host you want each pod to run on, or by using the daemon set, such that you're just always running one Cockroach instance on each machine, so that their IPs stay the same. And this is great because it works even if you don't have that pod-to-pod IP address communication between clusters, because you're just relying on the machines in each cluster having direct IP routability. And this has no moving parts, which is really nice. You don't need any sort of cross-cluster naming service. You'll just have to set up your join flags when you start nodes to include some of the machine's IP addresses. So I should clarify that when you start Cockroach and want to join a few separate nodes together into a cluster, you give each of them a join flag on the command line that says join to one or more of these addresses. And so you can specify IP addresses or DNS names. And when the Cockroach node starts up, it'll try to connect to those addresses. And if it can connect to any of them, it will join into the cluster that that node it connected to is a part of. And so for the join flags in the solution, we would just specify some of those machines' IP addresses that we're going to be using. And then once you set that up, you won't have to change them over time. The big caveat with this is that it depends on your host's IP addresses not changing. So this is especially a problem on cloud providers, because if you're using a hosted solution like GKE or EKS, they do node upgrades. They upgrade the Kubernetes software on each VM by just tearing down, deleting the VM and recreating it. And when it gets recreated, it's very likely to get a different IP address. And because we're relying on those IP addresses to stay the same, this could lead to problems. It could lead to the cluster, like a new cluster being started up, or nodes not being able to connect to back to the cluster after being restarted during these upgrades. So this is something you'd have to be very careful about if you're running on one of these clouds. You might need a special upgrade process, or you might need to modify the IP addresses while this is going on. Modify the IP addresses in the join flags while this is happening. So you have to be very careful while doing this. But I have run this for a while. In test environments, and it works really well because you get high performance because the nodes are just talking directly to each other. So it performs very well. And once you set it up, you don't really have to think much about it other than during those upgrade scenarios. And you want to be really careful on GKE, which can sometimes do automatic node upgrades if you don't configure it not to. So again, be careful if you go this route, but it is pretty reliable if you put in that care up front. And there's a bit of manual work involved in editing the configuration files to put in those join IP addresses, and assuming you want to run in secure mode, to create the certificates for each IP address. But overall, this is a totally fine way of doing it. And you'll also get maybe some extra reliability by doing it this way, because any sort of dynamic movement that Kubernetes would otherwise do to move your pods around and have to detach and reattach disks just kind of becomes a non-issue because none of that's happening here. And so there are some people that would argue that they don't trust Kubernetes to run their stateful services, who would trust something like this because Kubernetes isn't really getting in the way of things. However, if you do want to take advantage of more of Kubernetes features like rescheduling and health checks and all that stuff, this is a good solution that we do have some customers running in production that has worked quite well for them. It can be a little heavy to set up in the first place, but can work quite well after that. And what we do here is we run a stateful set in each cluster, and then we create a public load balancer for each CockroachDB pod. And this is something that's really easy to do in all the major cloud providers because they all have plugins for Kubernetes that make it really easy to expose a service from within a cluster. And so we get a separate load balanced IP address for each of the Cockroach nodes. So say we have 3 Cockroach nodes in our cluster, we'll get a separate IP address for CockroachDB 0, CockroachDB 1, and CockroachDB 2. And then we have to take those addresses from the load balancers and have all the pods connect to each other using those addresses. And we create certificates for all the nodes using those addresses. And since those load balancer IPs are stable, the underlying CockroachDB pods can be deleted and recreated, moved from one node to another, and so on and so forth. And the load balanced IP addresses will always route to the correct Cockroach pod. So this is great, and we have had people using this for many months, working well for them. And this is great because it works even when you don't have that pod-to-pod communication between clusters, just like in the previous solution. Because all communication between pods that are in different clusters is going through that load balanced IP address. And it continues working even as Kubernetes hosts churn in and out of the cluster. So it avoids that problem with the previous solution. Because even if nodes are being deleted and recreated all the time in the cloud, it's okay because the pods are still using the same load balanced IP addresses. And again, this doesn't require you to add any extra moving parts to your system other than the load balanced IPs. You don't have to run some service that allows the Cockroach pods in one cluster to be able to find the Cockroach pods in another cluster because you just have those those load balancers that are presumably being run by your cloud provider. There are some problems with this, of course, though, most particularly in how hard it is to configure, and like the fact that it adds some extra overhead on the data path, so it can be a little lower performing than things like the previous solution. Because on all but the most sophisticated load balancers, when you send a packet to that load balanced IP address, the load balancer will just forward it to any random host in the other Kubernetes cluster. And then that other host is going to have to look up where the pod is actually running and forward the packet to that host where the pod is actually running. Some providers are smarter, like I believe the load balancer integration on Google Cloud is smart enough now that the load balancer will send the packet directly to where the pod is running. But that's not going to be true everywhere. And so you might see slightly worse performance doing this. But most importantly is that it can be a pain to have to create a new load balancer every time you want to add a new node to your cluster. If you forget to do this, which it can be very easy to do, because you might just run the kubectl scale command, and then you'll see that your new pod isn't working because it doesn't have this IP address already configured for it. So you have to remember to do that. And it also can be expensive to run so many load balancers. So this will again depend on the cloud, but like creating this many load balancers on AWS could be quite costly. And you might not be able to do this on-prem if you don't have good load balancer integration between your Kubernetes cluster and some sort of manually run load balancer like HA proxy. And again, setting this up requires a lot of manual config file editing and certificate creating. So you get into some pretty advanced, complex configuration to make this happen. But once you set it up, it's going to be very reliable. I haven't heard of any outages caused by this sort of configuration. Just some hiccups while adding a new node to the cluster. But that didn't affect the currently running nodes, thankfully. The next solution, which you can do, is to, if you have direct communication between pods in different clusters, you can just let the pods advertise their internal pod IP addresses to each other directly. And of course, as pods get deleted and recreated on a new node, they might come back up with a different IP address. But Cockroach is able to actually handle this as long as the disk is moving around with the pod. So you can just rely on Cockroach's ability to handle node addresses changing to deal with the churn that will inevitably happen as pods move around the cluster. You'll also need to set up some sort of load balancer that can be used for the join flag, because we do need the join flag to have some sort of addresses that will always be there. But that join flag doesn't get used on the data path, and so this is actually quite fast because the pods are communicating directly with each other across the different clusters. And so the pros are that this is very fast. There's no overhead on the data path at all, other than the normal Docker overhead of bringing packets into a container and back out of it again. And this is very resilient to changes. You can add and remove hosts as much as you want, and this is actually really easy to maintain once you start it up. The only real caveats is that you need to have that direct pod-to-pod communication across clusters. And the biggest one is that it's hard to do this in secure mode. If you want to run with TLS certificates, it's tough to do, because Cockroach by default does hostname verification on certificates. And so the IP address that a pod is running at has to actually be in that signed certificate. Otherwise, other nodes won't trust it. And so we haven't tried running this in any sort of secure mode. We've only run it sort of as a proof of concept in insecure mode, because you have to have some sort of dynamic certificate creating and signing solution in order to create new certificates anytime a pod is given a different IP address than it had before. So this has worked really well for insecure deployments, and it's really fast and it's really easy to maintain, but setting it up for secure deployments is pretty tough. And so now we're getting to the thing that we actually have documented in our docs, and it's what I would call DNS chaining, which is a term I just made up. There might be a better word for it. But basically, we're taking that previous solution where pods are talking directly to each other on their IP addresses, which is great for performance, and we want to add some sort of persistent names to that solution. So we need some sort of persistent network addresses that will work even as the underlying pod's IP addresses change, because that will allow us to put those persistent addresses into the certificates for each pod, and then we can run in secure mode. And what we want to do here is somehow configure the built-in DNS server in each Kubernetes cluster to serve those DNS entries from the other clusters. But the question is how, of course, because kubedns is set up to only create DNS names for the services in its own cluster. One way to do this is to use core DNS instead of the default kubedns. So core DNS is a much more fully featured DNS server that allows for a lot more customization. It has a full plugin architecture. There's even an existing plugin called Kubernetes, which was written to allow one core DNS server to watch the API server of multiple Kubernetes clusters. So we could use that plugin to do exactly what we want. We could set up core DNS in each cluster to watch the services in all of our Kubernetes clusters. And then it would automatically create service names for the services in the other clusters. However, in practice, swapping core DNS in for kubedns on any of the managed Kubernetes offerings is very difficult. It's also difficult to modify each cluster's DNS domain. So you'll notice if you look at the full service addresses of Kubernetes services, they all end with .cluster.local, unless you've customized it yourself. And ideally, we would want each cluster to have a separate DNS domain so that it would be easier to distinguish between a service running in one cluster and a single service running in another cluster, so that you don't hit naming conflicts between them. And that's also apparently very hard to do in the managed service offerings. I tried for a couple days to do either of these things, to replace kubedns or to set up a different cluster DNS domain on GKE, and had no luck when we tried to do that earlier this year. However, core DNS is becoming the standard DNS server as of 1.13. So maybe this is going to get more feasible. Setting up a custom DNS domain might still be very difficult, so there would still be that roadblock. And unfortunately as well, the Kubernetes plugin that we would want to use doesn't come in the default core DNS Docker image that gets used. So it would still have some difficulties, but this is becoming more and more feasible over time as core DNS becomes the standard for Kubernetes. Another alternative, which I haven't fully explored, is to run core DNS alongside the default kubedns service. So we could configure kubedns to defer certain lookups to core DNS, and then have our own core DNS that's configured exactly the way that we want it, running in each cluster, watching the other Kubernetes clusters. And we could use some of core DNS's plugins or the rewrite rules to make the cross-cluster lookups work out. But I haven't fully tried this out, and I haven't heard of anyone else that's actually doing this. So if you're going to try this out, I think it would work, but you're going to be in uncharted territory. So just beware that I don't think this is very well tread ground. Also, what we to make this DNS chaining work, we could just take matters into our own hands. So instead of trying to use core DNS, we could just write our own controller that copies services from one cluster to another, and then they would automatically be populated into DNS. And since Kubernetes is just an API, anyone could do this if they wanted to. But it's much preferable to reuse existing solutions rather than build new ones, especially if I won't have a lot of time to dedicate to maintaining the new ones. So I haven't written anything like this. It seems like we should be able to use what's already out there rather than having to build something new. But this might be worth doing, and it would be a great thing to contribute to the community if you do have some time on your hands to try it. What we've ended up doing for systems like GKE and DKS is using what are called stub domains. So stub domains are a kubedns config feature that allow you to defer DNS lookups for certain domains to the name server of your choice. So we can configure a suffix that allows the kubedns in one cluster to redirect lookups for anything that ends in that suffix to a different cluster's DNS service. So if you have a cluster in US West 1B and you do a lookup for some DNS address that ends in US East 1B.cluster.local, then kubedns will know to just send that along to the DNS server that's running in that US East 1B cluster. So this is what I've put together some scripts for, and we've documented on our website for people to try out. And it's been most heavily tested on GKE. There are some great pros to this, right? So like the direct IP communication between pod solution, there's no overhead on the data path other than that normal Docker overhead, which is tough to avoid. And it's very resilient to hosts being added and removed. There's no need to configure a cross-cluster naming service. You're just using the built-in DNS. And there's actually no or very little manual work needed to get this running. We have a script in the CockroachDB GitHub repository that you can just fill in a couple parameters around where your clusters are running, and what their kubeconfig names are. And then you can just like hit run on the script, and in a couple minutes you'll have a running multi-region Cockroach cluster. However, you need to have pod-to-pod communication across clusters for this to work, and you need to set up some way for the DNS server in one cluster to reliably reach the DNS cluster in another server. So you can do this using like an internal load balancer on the various clouds, or you could use an external load balancer, or you could come up with your own solution for that. It's not great. On GCE, you today have to use an external load balancer because their internal load balancers don't work across regions. I believe they're working on fixing that, but I don't know when a solution will be around. And so that would be exposing your DNS server to the public internet, which probably has some serious security repercussions. You could put in some firewalls in place to keep that from being as much of an issue, but yeah, it's something to definitely be concerned about. You might end up needing to run your own load balancer, to enable these DNS servers to find each other on the network. And at that point, maybe you should just use that load balancer to handle the pod-to-pod communication. Finally, Istio is a project that has become very, very popular in the community over the last year or two. And you could use it to basically handle the naming of services across Kubernetes clusters, or even the routing of packets across clusters. And they've been working on this multi-cluster mode to handle this problem of addressing across clusters for the last half year or so. It was in the very early days when I was doing most of my experimentation earlier this year. It explicitly punts on the problem of like enabling pod-to-pod communication, though. All it's doing right now is naming. And what you do is you install the Istio control plane in one primary Kubernetes cluster. Sorry for that K7S typo. And then you have to install this special Istio remote component in all of your other clusters. And while I'll say that while this is super promising and hopefully will solve the problem next year, as far as I can tell, it's still pretty far from being suitable for production use. And I don't know of anyone using it with Cockroach to span clusters today. So it's under very active development, and it looks like it will improve quite a lot over time. And it has a very small overhead on the data path because packets go through the Envoy proxy, which is a very efficient, low-level proxy written in C++ that's in use at a number of companies throughout the industry. And like past solutions, it's very resilient to hosts being added and removed. However, the cons here are pretty heavy right now. It's running the entire control plane in a single Kubernetes cluster. And so if that region goes down, then you've lost your connectivity between clusters. It still has a single point of failure, and that hasn't been resolved yet. The setup process is really involved. I really struggled getting it to work. It took a few tries to get everything working correctly. And they even say in the docs that even if you follow all the docs until the end, running a real production environment would require additional steps, at least one of which is solving this problem of addressing between clusters for the Istio components themselves. They have this problem where if the Istio components in the main cluster get rescheduled onto different nodes and end up with different IP addresses, then those Istio remotes will not be able to reach them anymore. So you're actually just kind of like moving the problem from Cockroach into how you configure Istio. So it doesn't really solve things yet. And like some of these other, like the core DNS solutions previously, you have to copy the credentials for each Kubernetes cluster into the other clusters such that Istio can talk to all the API servers. It's a potential security risk. As always, though, Kubernetes is open source. It's an open API. It's really, really easy to program against, and so you can always do your own thing. You can set up your own DNS servers, use pod IPs with some sort of automatic certificate approver that you write, use core DNS as you please, set up your own proxy servers, and so on and so forth. And there are definitely some good options here, but it's tough for us to widely recommend any of them due to differences between environments. So to summarize, multi-cluster networking is pretty tricky. It's much more complicated than I would have expected, or than most people would expect. And unfortunately, not a whole lot has been done about it for years. This past year is the first year I've seen a lot of good movement in the right direction. And even after you nail pod-to-pod connectivity, so after you solve that first networking problem, you still have to solve the problem of providing stable names that work across clusters. But I am really excited about these different projects that have spun up that are starting to care about it, though. So you have the Cilium overlay network, which has the cluster mesh mode. You have Istio trying to solve the naming problem, and there are even companies like Upbound, which just released the cross-plane open source project, which is supposed to help you run applications across multiple clouds using Kubernetes. So it's hard to recommend a single answer for everyone, but out of these few solutions, there's definitely at least one of them which would be very reliable for you if you're willing to spend some time up front on setup. So thank you for tuning in for this webinar. If you have any more questions, I'll be answering some questions afterwards. And you can always find more information on our website or in our GitHub repository, or reach out to me via email or Twitter. So I'd be happy to take some questions now if anyone has any.
Fantastic. Thank you so much, Alex. We did get some great questions on the Q&A. So I just want to get started and ask you this question here. How can I tell if my clusters support pod talking directly between them?
Yes, so the easiest way to check if you have that pod-to-pod connectivity that I was talking about is to just try talking from one pod to another. So you can create a server pod in one cluster and run, say, a kubectl describe pod command on that cluster to see the pod's IP address. So kubectl describe pod will show you the IP address of that running pod, and then run a pod in another cluster that tries to talk to that first pod. And you can see if it works, then you have pod-to-pod connectivity. If it doesn't, then you don't. You could also try to dig through the docs if you don't have running clusters, but you're going to have to dig through the docs specifically for where your cluster is running or for the network provider that you're using. And in many cases, it's not called out very specifically in the docs. So I would recommend just going into the clusters, creating a pod in one and a pod in the other, and seeing if they can talk.
Great. Yeah, and I got another one here as well. How should I set things up if my clusters are on-prem?
So if you're running your clusters on-prem, I would most likely recommend that you use the first option I talked about, where you are statically statically assigning pods to nodes and using the machine's IP addresses directly. Otherwise, you might have to make sure you're using a network that can provide pod-to-pod connectivity across clusters. If you are just statically assigning pods to machines and using the host network, then you can be sure it's going to work no matter what you're using. If you're starting things from scratch, though, and don't have existing clusters, you might look into using the Cilium networking software in order, and then using the Cilium cluster mesh mode in order to get pod-to-pod connectivity, and then you can use something a little more advanced.
Great, and kind of related here, this one, is it possible to run across a mix of on-prem and cloud clusters?
Yes, you could run across a mix of on-prem and cloud. So you could actually use a different solution for each cluster if you want. So for the clusters that are running on-premise, you could statically assign each pod to a machine and use that machine's public IP address. And then in each cloud, you could maybe create an external load balancer for each pod and use that externally load balanced IP address. And those two should be able to talk directly to each other as long as you have set up connectivity between your on-prem and your cloud networks using a VPN or some other sort of solution to wire those together. Otherwise, you maybe create an external load balanced IP address for each of the on-premise pods as well.
Great. I got another one here. Is this the right place for storing certificates for LBs for secure connection? Currently, we're storing it in PV. Is this the right way?
You're storing the certificates in PV. So traditionally, certificates would be stored as secrets, but there are some concerns historically around the security of secrets in Kubernetes as well, because they're not encrypted on disk by default. So there's nothing fundamentally wrong with storing your certificates on the PV. You'll just have to regenerate them if, for some reason, that PV gets lost. But there's nothing wrong with that. In the setups I've been doing, I've been storing them as secrets, though.
Cool. And just the last one here today, so far at least, is what is the communication protocol between the DB nodes? Is it pure HTTP (S), or would it be possible to use KH then?
Could you repeat the last part of the question?
Yeah, would it be possible to use KH or KH then? And then there is a link here as well to GitHub, so it is also something we could follow up with.
So yeah, I'm not sure what the alternative being proposed is here, but I can say that the nodes communicate directly to each other using gRPC, and that can be encrypted via TLS certificates. And so we strongly recommend when you deploy Cockroach, you deploy it in what we call secure mode, which uses TLS certificates to encrypt all communication between nodes, as well as between clients of the database and the database nodes. And so all communication will be encrypted directly inside the node process before being sent out over the wire.
Great. We did get one more in here. Does static assignment of pods respect resource scheduling?
Static assignment of pods. So the pods will always be assigned to that machine regardless of whether or not there are enough resources. I'm not sure offhand whether the pods will start without the resources being there, whether it'll cause resource evictions. I haven't tried that. That's a really interesting question, because Kubernetes does have a sense of which pods are considered more important than others, and will prioritize putting those in first. But I don't know, and we can follow up with you if you're curious.
Awesome. Well, again, thank you, Alex. This is all the time we have left today, and I also want to thank our audience. Thank you guys for showing up. You really made this content come alive, and we love your questions. So keep an eye out on our next webinar invite, and in the meantime, also look out for the recording that will come through soon, so that you can either watch it again or share it with your colleagues. So yeah, have a great day, everyone.